All right, so for those of you who are wondering, a question is, hey, somebody misspelled sine and cosine. So these functions are, I heard this pronounced usually as sinh, and this one is pronounced as cosh. And what are they? Well, cosh is e to the x plus e to the negative x divided by 2. And sinh is e to the x minus e to the negative x divided by 2. So if you look at the sinh function, it looks something like this. So this is what the sinh function looks like. If you look at the cosh function, it looks a little bit like this. So this is cosh. So does anybody know where you see a cosh curve out in the wild? So we'll add some drawing here. That will be very suggestive. Have you seen anything like that out in the wild? Yeah, so actually the cosh curve is what you see if you see a hanging wire. So for example, Golden Gate Bridge. So this curve here is the cosh curve. Now there's a couple ways to think about this. So you can think of cosh, sometimes they call this the even part of e to the x. So in other words, it's not an even function e to the x, but if you were to think about e to the x, you can split it into something which is an even function and an odd function. And so you can check a couple things. Namely, if you add sinh plus cosh, what do you end up with? You actually end up with e to the x. Cosh is an even function, and sinh is an odd function. Now you might say, this looks great, but this looks like nothing like cosine, and nothing like sine. Except, they are. It turns out, weird stuff, and this gets a little bit complex. If you were to allow complex numbers and you were to put I times x into the hyperbolic cosine, what do you think comes out? It turns out it's the cosine function. So that this function, which looks nothing like the cosine, actually is the cosine function, just in a sort of a different slice. If you were to say, oh, cosine, you can allow complex numbers in as well. Now, if you let sinh and you put I times x in, what do you think comes out? Yeah, you would think so. But it's actually I times sinh ix is the sine. So that's why they're called sinh and cosh, because they're actually related to the sine and cosine if you allow complex numbers. So if you do see these problems, see these functions on homework, it just means replace them by the e to the x plus e to the negative x over 2 and go from there. That's what you would do. A couple of fun facts. What's the derivative of sinh? Cosh. What's the derivative of cosh? Sinh. Yeah, there's no plus minus anymore. These are even better. Okay, so that's that question. All right, we should get to the new material. Okay, so where are we at? So we are talking about systems of differential equations. And the idea is we're used to sort of a single variable equation. So one equation, differential equation. So x double prime plus 5x prime plus 22x equals 7t cubed. Something like that. Those are the kinds of things we've talked about. But now we're in the same where we say, oh, there's multiple functions involved. And actually, what it makes us really exciting is that they can interact with each other. So somehow what's happening with the function x also has an effect on the function y. We saw some examples of this last time, where they said, oh, maybe there's some objects connected by springs, where if you move one object, well, that will cause the other object to move as well. Or maybe you have several tanks mixing together, and there's pipes connecting the tanks. And so what's happening in one tank affects what's happening in the others, because they're connected. Things move together somehow. Now, one thing that will be true for us is that the number of equations involved will be the number of functions. So, for example, if I have a system where I have an x and a y, I'll have two equations. I won't think this as there's an x equation and a y equation. I'll think of this as, well, there's two equations and x and y are involved in both. And so if you think back to algebra, you're like, oh, I have two equations and two unknowns, and we're trying to solve. And yeah, it is like that, but of course, more interesting because now we have derivatives in the mix as well. Now, last time we said, well, suppose you have a high order differential equation. So in other words, you have an expression of the following form. The nth derivative of a function is this piece here. Now, normally when we write this, it sort of makes us shut down our brain and be like, this is just some weird symbol. But the way you should interpret this is that when you see something like this, you should just say, this piece over here is just a shorthand notation for some combination of these symbols here, t, x, x prime, all the way up to the n minus first derivative. So if you just see this expression here, f of a lot of stuff, that just says, oh, there's some expression. And we just don't know the expression in this particular case. We just want to write something in general. And one of the things we said is we can transfer this into a system where the highest derivative we have to look at is the first derivative. And it's actually not so hard to see. In fact, you can kind of cue off of this what's happening. So what happens is that the function x, we call that x1. And then we say, okay, well, function x prime becomes x2. And we just keep working our way over. X double prime becomes x3, all the way to the very end, where I run out of good colors. And so, well, okay, so x n minus first derivative is xn. And so we say, well, once you replace those, it's this nice correspondence. And you can say, well, this n minus first derivative, one more derivative gives me my nth derivative. That's where the xn prime becomes the nth derivative of x. And then I have the fact that all these things are related by derivatives one from another. Sort of a ladder of functions working our way up to high order derivatives. So there's an observation that says, hey, I can transform something which has a high order differential equation. In other words, this kind of expression, one equation, nth derivative, into a system of first order equation, which is what we have here. So this is a system. When you say system, just think of it as a collection of them. And there's n equations here. They're all first order. And then there's this sort of comment. The opposite can also be true. Now, what do we mean by the opposite? Well, that says I can go from a system, in other words, a collection like this, and I can go to a single ODE. So that way, we can say, oh, we can fall back on tools we've already used before. Now, we don't want to do this all the time because then it feels like we haven't gained anything. But at the start, that's how we'll start. Because it says, well, I want to say, can I reduce to something I've seen before? This is a really good way to go about solving problems, is to say, well, I don't know, I haven't seen this, but can I change it so that it looks like something I've seen before? So let's do an example. Solve the following system of differential equations. So we have x prime is 3y, y prime is minus 12x, and there are some initial conditions for x and y. Now when we say solve a system, what is it we're trying to find? We're trying to find x and we're trying to find y. So we've got to find both the functions. All right, so how do we begin? And keep in mind, we're trying to sort of embrace this idea. Can we somehow, instead of having two equations with two variables, can we get down to one equation with one variable? if it helps, put on your algebra hat. When you're solving two equations with two unknowns, what are some things you can do with two equations and two unknowns? What? Substitution. Okay, so people are saying substitution can work. Well, what does substitution mean? Well, it means you can go and you can say, I can solve for one of the variables, and then I can substitute it into the other equation. All right. Well, you might say, but look, that's a y. That's a y prime. That's an x. That's an x prime. So nothing is quite matching. That's okay. No problems. No problems. Because if x prime equals 3y, taking derivatives, what do we have? X double prime equals 3y prime. And now we say, look, good news. I can go to my second equation, y prime equals minus 12x, and use that to replace the y prime. So we'll have 3 times negative 12x, which is negative 36x. This can also be written as x double prime plus 36x equals 0. So what have we done? We started with two equations, two unknowns. They were both first-order differential equations, but they involved two variables. Well, how many equations do we have now? One equation. How many unknowns? Just one. But we had to compromise. How many? What's the order now? It's 2, it's second order. So, okay, so we have a higher derivative involved. But the good news is we got back to something we're comfortable with. Something we can solve. So where do we go from here to solve this? Sorry, what? Okay, so we're going to go to the characteristic polynomial. Put in the r. So this is r squared plus 36 equals 0. So what are our two roots? Plus or minus? 6i. All right. Well, it looks like this one's going to be a little bit complex. All right. So what does our general solution for x look like? So we have our roots, so we can write down what x should look like. So I'll just use a, but yeah, you could also use c1. So when it's complex roots, there's cosine and sines, and these are pure complex. There's no real part. These are pure imaginary, so it's just cosine and sine. So a cosine 6t and b sine 6t. Now, we need to solve. So how do we solve for a and b? I mean, in general, how do we solve for a and b? What do we look for? What's our initial idea to help us solve for these? Oh yeah, initial values. That's right. Okay. So do we have any initial values? Yeah. What do we have? We have x of 0 equals 3. Nice. So x of 0 equals 3. What happens when we plug 0 into the a cosine 6t plus b sine 6t? What does it become? Oh yeah, eh? Oh sure, yeah, eh? No problem, eh? Right? Just a, because cosine of 0 is 1, sine of 0 is 0. And so, hey, we solved for a. A is 3. Wonderful. Okay, now, we have a quandary here. This is y of 0. That's not an initial condition involving x. What is it we really would want now? Well, we would really love, if we were just thinking about this as solving for x, we'd really like to know what is x prime of 0. do we have any way to solve for x prime is 0? Okay, I hear yeses, so how do we do it? Sorry, what? Okay, x prime is 3y. So x prime of 0 has to equal 3y of 0. And we do know y of 0. So that says x prime of 0 is 12. All right, so let's take our x prime of t, derivative of a times cosine 6t. Negative 6a sine of 6t. And then derivative of b sine of 6t. 6b cosine of 6t. We plug in 0. And we know x prime of 0 is 12. On the other hand, what else does it equal? 6b. So what does that tell us about b? b is 2. And now we're like, hey, we know a. We know b. And we come to the conclusion that x of t is equal to 3 cosine of 6t plus 2 sine of 6t. And we circle our answer. Are we done? No? Uh-oh. I put a circle here. There is a suspicious space. There is. Okay, so how should we fill this suspicious space? Well, the answer is we're solving the system, which means we need to solve for y. So, how do we go about solving for y? Well, one thing is we could repeat the whole process, but that sounds like work. Is there anything we can do to sort of shortcut? Okay, so we know x prime equals 3y, someone said. So that tells us that y is equal to 1/3 x prime. Because we can solve for y. Okay, well that tells us that we can say, okay, that's 1/3. And we actually know what x prime is, because we know what a and b are. So that's negative 18 sine of 6t plus 12 cosine of 6t. All right, so divide by 3 and maybe change the order so they match. 1/3 times 12 makes 4 cosine 6t. 1/3 times negative 18 makes negative 6 sine of 6t. And now we are done. We've solved for x, and we solved for y. All right. Good. Good. So we can do these problems, hopefully. All right, now, where are we going? So another wonderful wall of text here. And I don't want you to be intimidated by this. We'll talk our way through it. This is the Cliff Notes version. So here's the takeaway. This part is what we did before, where we said, oh, a linear first order equation, the kind of equation that we liked at the very start of the semester. X prime is some function of t times x plus some other function of t. The punchline is we're going to go to a linear first order system, and it's going to look almost the same. X prime equals a of tx plus f of t. Except they have slightly different things involved. Whereas these are functions that are really, the outputs are numbers. These are going to be more interesting. Okay, so where are we going? So our goal is to say, what kind of things do we like? And we like first order. That was one of the things we just talked about. It says we can make everything first order. And we like linear. Now, linear in the sense of, in terms of the variables. So when we talked about linear before, we said, well, if I have, say, a differential equation in terms of x, I'll have an x prime, and x double prime, but they don't mix together. So it's not like I have x prime times x double prime or x to the 4th power or anything. It's just combinations of them in a very clean way. So we're going to be in that same setting. So in particular, we're going to say we have this, and this is it looks intimidating at first, but but don't think too much about it right now. Just sort of let it absorb into you. Let it become one with you. So we have our functions, x1 through xn, that we're trying to solve. In its first order, which means that we're looking at the derivatives of those functions. And we say, okay, for any particular function, we'll focus on, say, x1. What it looks like is some nice combination, and nice here being linear, of the functions x1 through xn. So the a11, a12, and so forth, so on. These are just coefficients. Now they could be numbers, that's the nice setting, or they could be some functions of t, but they're only functions of t. And then there's the piece on the end, which is just sort of a function of t. So you should think of this as sort of the non-homogeneous part. So if this were gone, that would be homogeneous. If it's there, it's non-homogeneous, is how you should think of it. All right. So where are we going? Well, what we're going to do is we're going to group these objects. So for example, f1 through fn, we're just going to group them together in an object called a vector. In a similar way, we're going to take our derivatives, that what we're trying to have on the left, we'll put those all together again in a vector. And then this expression right here, what we're going to do is we're going to put it in a format where we gather all the coefficients together in this array, which we'll actually call a matrix. And then we'll have the functions, again, all as a vector. Okay. So it's a shorthand. So we have this matrix will be a matrix that depends on t. And what that means is just the entries are functions of t. This vector is the vector of the functions that we're looking for. This is our vector of our non-homogeneous part. And then we have this vector, which you'll notice if we label this vector as x, we call this vector x prime. Now, why do we do that? And this is where the fun fact comes in. And that's, fun fact says, what does it take to do a derivative? It turns out there are three things involved to do a derivative. And as long as you can do those three things, you can take derivatives. You need to be able to add, you need to be able to scale, and you need to be able to take limits. And it turns out that with matrices, you can do all three of those things, which means that we can take derivatives of matrices. And the way you do it is you just take the derivative of each entry. So if this vector, which we shorthand call x, we take the derivative of that, well, it'll just be take the derivative of each entry. So that's how you get x1 prime, x2 prime, all the way to xn prime. So that's why we call this x prime. So the moral is that this linear first order system is the collection of functions that we're looking at, in particular the derivatives of those functions, is equal to a matrix of coefficients times the vectors of the functions that we're looking for, plus possibly a non-homogeneous part. So that's how we do our translation. Now, I hope that you're familiar with matrices a little bit, and if you're not, you'll get familiar with them really soon, because we're going to spend the next couple of sessions delving into matrices and how they work. And in particular, one thing that you will discover is how you do matrix multiplication. So the way it works is we're going to go along a row and down the column. So you would have A11 times x1, which is that entry, A12 times x2, which is the next entry, dot, 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 and finish with A1n times xn. So this collection is just a shorthand notation for this system. So even though it doesn't look like there's a lot of text here, it's just another way of saying something that looks like this. All right. What do we care about? Well, one of the first questions we often have when we're looking at differential equations is this even a question we should bother with? Does it exist? And if it does exist, is there only one? And we said when we were working with our linear first order equations back in our old days when we were so innocent, we said, yeah, it exists. And it turns out it's still true. So if we're dealing with this more complex setting where we have linear first order systems, it's still true that we have existence. And that extends for as far as we can go with the functions being continuous. And when we talk about the functions, the pieces that are inside of A and what's inside of F. Now, where are we going to be going? Well, our destination for the next few weeks is developing the tools of how to work with matrices and saying, okay, what's going on? How can we use that to solve? That's what we want to get to. How can we use tools of linear algebra, or if you like, tools of matrices, to help us solve? And the ones that we're going to really like, in fact, is that when we look at this A of t, because right now we're saying these are functions of t, we say, oh no, we'd really like them to be constants. In other words, the constant coefficients setting. We're really going to like that. All right. So that's our setting, and that's where we're going. Oh, cool. Any questions? Are you ready to try some more problems? And I will say it'll take us time to develop our full set of tools. So don't be overwhelmed. We're just going to ease our way into it. So, an example. Find the particular solution of the system by reducing to a single differential equation. So this is still what we've just talked about before. We're just taking it up just a notch. In other words, when I say before, our first example. So our idea that worked then is substitution, and it should still work now. I think that's the right spelling of substitution, but that feels like there's a lot of T's there. Substitute, yeah, okay, that seems good enough. All right, it's not an English class, I can misspell. I'm allowed. I think even in English classes they misspell, so. All right, so x prime equals 4x minus 3y, y prime equals 6x minus 7y. What do we do? What do we do? If only there were an idea. What could we possibly be doing? Oh, we could do substitution, right. Okay, good. Great idea. All right, so let's look at the first equation. Is there a variable we should solve for here? What? Well, the reason I'm asking the question is because that's how substitution works. You solve for a variable, and then you substitute. That's why I'm asking the question. So is there a variable we can solve for in the first equation? No, we don't solve for x. No, it was actually the variable y. Ha ha ha. Punchline. All right. Ba-dum-bum. All right. Now, in some sense, you might say, why do we solve for y and not for x? Well, how many x's are there in this first equation? There's really like two x's. There's the x and the x prime. But there's only just one y, so that's great. We'll get that y by itself. 3y is 4x minus x prime. I don't like fractions, so I'm not going to divide by 3. Unless I absolutely have to. So I like to avoid fractions if at all possible. So now the idea is say, hey, let's plug this notion for y into the second equation in both the places where y shows up. Now, because there's a 3 attached, before I do that, I'm going to multiply the second equation by 3. So 3y prime is 18x minus 7 times 3y. So I've multiplied 3 by 3 just so I'm compatible with the fact that I wrote 3y. What does 3y prime become? Because this is 3y, what does 3y prime become? 4x prime minus x double prime. Because to get from 3y to 3y prime, take a derivative. Derivative of 4x, 4x prime. Derivative of x prime, x double prime. Equals 18x, subtract 7, And the 3y, well, that's 4x minus x prime. And now we're happy in some sense. We're like, look, we got down to a single differential equation, which is what we wanted to. We're not done. We still have to find a solution, but we've made progress. Okay, so let's expand a little bit. So 18x, let's see, minus 7 times 4, minus 28. Minus 7 times minus x prime, plus 7x prime. All right, what's the next thing we should be doing? Move everything to one side. And I want to have the coefficient for x double prime to be positive, so I'm actually going to move those over. So I'll start by writing x double prime. When I move it over, there'll be 1x double prime. What's the coefficient for x prime? 3x prime, right? Because there's 7 here and I subtract 4. So plus 3x prime. What's the coefficient for x? Minus 10x. All right, so that's an equation. And we're going to refer back to this equation later on. So I'm just going to put a little halo around it. That's saying this is important. We'll come back to this in a little bit. But we keep going. Okay, so what's our next step? Characteristic equation or auxiliary polynomial. So we do the r's. What does this become? R squared plus 3r minus 10 equals 0. Okay, does that factor? Fingers crossed? Yes. Yes? Oh, good news for us. Great. How does it factor? R plus 5, R minus 2. Should always double check. R squared, that's a good sign. Minus 2r plus 5r is in fact 3r, and minus 10. Yeah, that all works out. The math checks. Good. So what is r? Minus 5, positive 2. So what does x look like? A e to the negative 5t, b e to the 2t. Okay, so now we have the form for x. Well, we need to solve for a and b because we have to find the particular solution, and we have some initial conditions. So we have the fact that x of 0 equals 2. Going back to the previous problem, what also would we like to have in addition to x of 0? We'd like to have x prime of 0. So what can we say about x prime of 0? Can we figure that one out? Yeah, see how we have that x prime there? So that's 4x of 0 minus 3y of 0. Well, x of 0 is 2. Y of 0 is minus 1. So that's 4 times 2 minus 3 times minus 1, giving us 11. Yeah, it's 8 plus 3. 11. Okay, so we're getting close. X prime of t, well, that's not so bad because these are nice functions. So we can write those down. So namely negative 5a to negative 5a e to negative 5t plus 2b e to the 2t. Okay, what happens when we plug 0 into our function? What do we have? So what? Yeah, a plus b. So a plus b equals 2. Nice! When we plug x prime is 0, which is 11, well, what happens when we plug 0 into x prime? Minus 5a. Plus 2b. Okay. So now we're in a setting where we have two equations, two unknowns. This will often happen, but this is sort of the nice setting of two equations, two unknowns. And this is the kind of equation that we're like, yes, we should be able to just sort of power our way through this and figure out what to do. So what do we do? Okay, so one person has suggested you can do substitution, like what we did substitution at the start. Is there anything else other than substitution? Because there is something else I want you to get comfortable doing. Elimination. Okay, so elimination, the idea of elimination, in case you're trying to remember what does that mean, is you want to multiply one equation by some value, the other equation by some value, so that when you put it all together, you get cancellation. So, anybody have a suggestion on what we should be multiplying by? You want to multiply the top one by -2? I think is what people were saying. The bottom one just is going to stay the same, but then we're just going to multiply by that by 1. If we do this, we'll have -4 plus 11, also known as 7. We'll have -2a minus 5a minus 7a minus 2b plus 2b, 0. That's how elimination works. You eliminate a variable by appropriately combining these together. What does that allow us to say about the value for a? -1. Once you know a, you can go back to either equation. Usually you go back to the one that looks simpler. 2 is equal to -1 plus b. What does that let us say about b? 3. Okay, so now we know a and b. That's all we needed to know to find x. So we have that x of t is equal to a, which is minus. So minus e to the minus 5t plus b, which is 3, e to the 2t. And we're done, right? No. What else do we need to do? Solve for y. Okay. Well, where do we solve for y? Now we can go back to the very beginning then when we talked about our substitution, which allowed us to say what is y in terms of x. Because we spent a lot of time to find x. Well, let's use that time to our advantage. So we could say that y is 1/3 of 4x minus x prime. Okay, so that's 1/3 of 4 minus e to the minus 5t plus 3e to the 2t. So I'm just copying what x is. Subtract x prime. So that's, okay, so yeah, 5e to negative 5t and 6e to the 2t. Okay, so let's be careful here. How many e to the minus 5t's do we have? There's -4, -5, making -9, times 1/3, -3. How many e to the 2t's do we have? Well, there's 12 here. Don't forget the 4. Subtract 6. That brings 12 minus 6 is 6, times 1/3 is 2. So now we have y. So y of t is equal to -3 e to the minus 5t and plus 2 e to the 2t. Now I should pause and say, if we had any doubts at all about whether we did this problem correctly, what could we do at this stage? We can take these functions and check, do they satisfy this equation and this initial condition? And if they didn't satisfy this equation and this initial condition, what would we do? We'd check our work. Or we'd say, well, partial credit, move on to the next problem on the exam. But probably we should check our work first before we embrace the partial credit mantra. But the point is, we can still check whether something is a valid solution. All right. So we're going to look at a slightly different way that we can think about doing this problem, which can help us solve problems that we can't do by straightforward substitution. And to get there, just to call back to Cramer's rule. So we talked about Cramer's rule before. Now, we're essentially going to look at something which is the same thing as Cramer's rule, but it's going to be a little strange. I'm going to be honest with you. The first time you see this, you're going to be like, this feels strange. And the second time you see this, because we're going to do it again next time, this feels even stranger. But after you do it a couple times on the homework, you'd be like, okay, I'll accept it. So the setting, and the reason why this is going to feel unusual, is we're going to look at matrices again, so that's not too surprising. This kind of has a feel for what we were talking about before, where we have some matrix times x and y is some function. But the matrix here has strange pieces in the sense that what we're calling these L's are polynomials in D. Now, what is D? D is just a standard for saying take a derivative. And so if you see something like d squared minus 4d plus 1, well, if I were to take d squared minus 4d plus 1, and I were to times that by x, what would I have? X L prime minus 4x prime plus x. And so in particular, there's a technical term for this in that this is not really a function. This is what we call an operator. And what is an operator? Well, an operator is something which acts on an object. So it needs a function to do something to. So I can't, if I just talk about what is d squared minus 4d plus 1, it says, well, it's something that has to act on something. You have to feed it something. We feed it an x and it says, I know what to do with that. And out comes this new expression. So you have to have something for it to act on. So in this case, it acted on x. Now, what if I put y there? What would be the change? What would come out? So if this was a y, what happens over here? Yeah, y double prime minus 4y prime plus y. So it's whatever you put in here, you just follow the rules. This says take a second derivative, subtract 4 times the first derivative plus the original thing. Okay, so suppose we are in this setting where we have this collection of operators multiplying by x, y equals f of t, g, t. So in some sense, this is like a derivative. This is saying I'm taking a derivative of these pieces in some way. Now, if you look on this and you say, well, hey, that's kind of like the same kind of setup we had when we were talking about solving in Cramer's rule, where we had a system of equations and unknowns. And in Cramer's rule, you said, okay, you take the determinant of the original matrix, which is this piece, and then you take the determinant where you replace the column. Say if I were solving for x, I replace the x column by what you wanted to get. If I was solving for y, I replace the y column by what we want to get. Now, the thing that makes us different from Cramer's rule is where was this determinant before? If you think back to Cramer's rule, how did it look? Yeah, it was on this side being divided by it. You might say, okay, so why did you change it so that you wrote it in this way? Well, the moral is this expression here, which is the determinant, it's an operator. If I'm an operator, what do I need? I need something to operate on. I need an operatee. Wait, that's not a word. Okay, we'll just say something to act on. So that's why I have to put it on this side so it acts on the x. If I put it downstairs in the denominator, it's nonsense. It's nonsense. And we don't want nonsense. We want sense. That's why we take math classes, because we want things to make sense. Okay, so let's talk about our previous problem. Now, our previous problem, I really mean this problem that we just worked through. So, start with this equation. X prime equals 4x minus 3y. Let's move all the variables over to the left-hand side. So you'd have x prime minus 4x and plus 3y. Similar, if you take this equation, move everything over, minus 6x, y prime plus 7y. Now you might say, why did you put the x in front of the y's? Well, I really want to group the x's together and the y's together. Okay, so this system of equations is the same as the one we just did. All right, we're going to come back to this page in a moment. Now, using our notation for derivatives, x prime minus 4x is the same as d minus 4 times x. You can check, right? D times x means take the derivative, so that's where you get the x prime minus 4x. And 3 times y, it turns out, true story, is 3 times y. Minus 6 times x, minus 6 times x. Again, here's a derivative, so that's d plus 7 times y equals 0. And now if you look at this, you say, oh, I could think of this as a matrix where these pieces are my coefficients. So you put that in a matrix, times xy, 0, 0. So we're right into the kind of system we were hoping to get. So if this were true, then that would say that if we take our determinant of this matrix with little operators inside and apply that result to x, that should be the determinant if we replace this column by zeros. Well, is it true? Let's find out. So let's take the determinant. What's the determinant of this? Well, d minus 4 times d plus 7, let's just start there, right? Because you do the diagonal, subtract what? Subtract negative 18. And so this determinant is itself an operator, equals, now what happens over here? 0 and 0. So we get 0. Okay, d minus 4 times d plus 7, what does that become? D squared plus 3 times d minus 28. And then we have minus 28 plus 18, which makes that minus 10. So that's the determinant of this thing becomes the operator d squared plus 3d minus 10 applied to x. But what's another way to write d squared plus 3d minus 10 times applied to x? X double prime. Plus 3x prime. Minus 10x equals 0. Now, have we seen x double prime plus 3x prime minus 10x equals 0 before? And we have! Wow! That's cool. It's the same thing. And you're probably like, but that wasn't so hard to find it originally that time. But we will have times when it's really hard to find it. So this just says, hey, it does work. The machinery works. Okay. So now we'll try to get something using this. And we're going to go a little bit at a pace here just because of time. So find the general solution for this system. So we don't have to find our particular solution because we don't have initial values. So if we wanted to apply this technology, sometimes this is called the method of elimination, well, move the variables across. So x prime minus 2x minus y equals 0. That's the first equation. Here you'd have minus x plus y prime minus 2y. And this part, the minus e to the 2t, you leave that on the other side. That's the g of t. So if it's only involving t, that stays on the right. But if it's the variables, you move them to the left. Now, x prime minus 2x, in terms of this notation with the letter d, what does that become? D minus 2. Minus y is just minus 1. Minus x, minus 1. Y prime minus 2y, well, it's the same thing as x prime minus 2x. It's just you swapped x and y, so it's the same kind of operator. So it's still d minus 2. So this becomes, once you rewrite it in our notation here, this matrix, which involves these operators, times this vector xy equals this vector 0 minus e to the 2t. All right. Do you want to solve for x? Let's solve for x. So according to this rule, we take d minus 2 minus 1 d minus 2 times x is equal to, on the other side we have 0 minus e to the 2t and minus 1 and d minus 2. All right. What's the determinant? D minus 2 squared plus, yep, minus 1, you're right. X. What's the determinant on this side? Negative e to the 2t. Well, d minus 2 squared, that's d squared minus 4d plus 4, but plus 4 minus 1 makes it plus 3. So we have x double prime minus 4x prime plus 3x is minus e to the 2t. And now we're kind of in our happy space, because this is the kind of differential equation that we know. Are you okay for me going for another couple minutes, or should we just stop? And you can finish on your own. Go for like another 2 minutes. All right, let's just, we're good at this stuff, right? Because this is our stuff we're good at. All right, what's the characteristic polynomial? R squared for r plus 3 equals 0, because we're doing the homogeneous. And it factors as r minus 1, r minus 3. Which says that x of t has the form some constant e to the t, some constant e to the 3t. Now, the non-homogeneous is e to the 2t. Are we happy? Yeah, we're happy in the sense that we don't have to worry about any bumping. No bumping required. Woohoo, yay, no need to bump, no need to bump. So our particular solution looks like, well, next letter of the alphabet, some constant e to the 2t. So to find the c, plug it in. So we're going to take our c e to the 2t double prime minus 4 c e to the 2t prime plus 3 times c e to the 2t. That's going to be minus e to the 2t. Well, it's not so hard to take the second derivative of e to the 2t. So that'd be 4c e to the 2t. First derivative would bring it 2 down. And don't forget the minus 4, so minus 8c e to the 2t. And then you'd have plus 6, sorry, not plus 6, plus 3, because there's no derivative. 3c e to the 2t is minus e to the 2t. 4 minus 8 plus 3 is negative 1. So minus c e to the 2t is minus e to the 2t. So what can we say about c? C is 1. So when I said x is here, I really should say x homogeneous part. So our real function for x is some constant e to the t, some constant e to the 3t, plus e to the 2t. Now, the other thing we have to do is do what? Find y. What's the best way to find y? We can repeat a lot of work, or we can say, hey, y looks like x prime minus 2x. So we'll just do that. Okay, so what's x prime look like? Well, that's a e to the t plus 3b e to the 3t plus 2e to the 2t. So if I take x prime, subtract 2x, I'll have a subtract 2a is minus a. If I have 3b subtract 2b, that's b. If I have 2e to the 2t, subtract 2e to the 2t, that's 0. And that's our final answer. So that's the solution. All right. Next time, a more interesting example.